we kind of have, watch that. Okay. The first one is a long division example. We're dividing a polynomial by a polynomial. And you might recall that what we did with that is we had to set it up like a long division problem. We have to put the 2x minus 2 on the outside. Long division. Here's our dividing sign. And on the inside, we have to put what we call the dividend, the thing that we're dividing into. But we have to be very careful that our polynomials are in descending order. And that means I have to rearrange the terms of this top polynomial. The first thing has to be the 6x to the third, because that's the highest power. Next is the negative 8x squared, then the x term, which is minus 2x, and finally plus 11. Notice I have all the terms, I just had to put them in the proper order. And then, if you recall, what we do is we take our first term, which is the 2x, and divide it into the first term. So 2 into 6 goes 3. X into x squared, remember we're subtracting x from 3 minus 1 is 2. So the first thing I get is a 3x squared. I put it on top. You don't have to be too careful about where you place it on the top. It just has to be on the top. You take what your answer that you just put up there, the 3x squared, and multiply it by your divisor. So you take the 3x squared and multiply it by the 2x. That gives you 6x to the third. And the 3x squared times the negative 2, that gives me a negative 6x squared. Okay, so we remember the steps. Divide, multiply, subtract. I am now up to the subtraction. I have to subtract the 6x cubed minus 6x squared from the top. So remember what I told you to do when you want to do algebraic subtraction, which means you're going to change signs. This is originally a positive because it has no sign, so it'll become a negative. This is a negative, so it's going to become a positive. And now we have 6x cubed and negative 6x squared, which together cancel out. And here I have a negative 8x squared and a plus 6x squared. Negative 8 plus 6 gives me negative 2x squared. Okay, after I subtract, I bring down the next term, which is negative 2x. And start the process again by taking the first term and dividing it into the first term. So 2x into negative 2x squared gives me negative, well, the 2's cancel out, and x into x squared is x. So it just gives me negative x. I put that negative x on top, and now I multiply by what I just put on top, which is the negative x. Negative x times 2x is negative 2x squared. Negative x times negative 2 is positive 2x, because the negative and the negative give me a positive. Okay, I now subtract. So this one is going to become plus, and this is going to become minus. So the negative 2x squared and the plus 2x squared cancel. And here I have a negative 2x and another negative 2x. Remember, I always use a new sign, which together give me negative 4x. And I bring down the next number, which is the plus 11. Always bring down, that's why you have to be careful with this. You have to be really neat. So now I take the 2x and divide it into the negative 4x. So 2 into negative 4 gives me negative 2. And the x's cancel each other out. Now I take what I put on top, which is negative 2. Negative 2 times 2x is negative 4x. Negative 2 times negative 2 is positive 4. And again, I have to change the sign so I can subtract. So this is going to become a plus, and this is going to become a minus. The negative 4x and the positive 4x cancel. And positive 11 and negative 4 give me 7. That means my remainder is 7. So I take the 7 and put it over the 2x minus 2, which is the divisor. And here's my answer. Any questions about that? Okay, so let's go on to the next question. The next question was how to deal with something that has negative exponents. And I'll remind you of the steps. When you have an expression that has exponents, the first thing you want to do is get rid of the parentheses by distributing the exponents. You have to understand the 4 and the 1 understand to have exponents of 1. So when I distribute the exponents, I'm going to get a 4 to the negative 3, because 1 times negative 3 is negative 3. And x to the negative 2 to the negative 3. Remember, we multiply their exponents. That gives me x to the 6. And on the denominator, 3 to the 1 to the negative 3 gives me 3 to the negative 3. And x squared to the negative 3 gives me x to the negative 6. I just multiply the outer exponent by each of the inner exponents. So as I said, I distribute that exponent. My next step is to get rid of negative exponents. After I remove my parentheses, I only want to work with positive exponents. When I'm simplifying, I don't want to be left with negative exponents. So at this point, I'm going to get rid of the negative exponents. And I do that by remembering that a negative exponent means that you're supposed to be taking its reciprocal. And in order to take its reciprocal, it means that what you're going to do is if something's in the numerator, you're going to move it to the denominator. If something's in the denominator, you're going to move it up to the numerator. So I'm going to look at each one of these numbers and letters, each factor, and deal with it. The 4 has a negative 3 exponent. So I have to move it to the denominator to make it 4 to the positive 3 because we have to take its reciprocal. The x to the 6th exponent is positive, so I'm just going to leave it on top. I don't have to move something that has a positive exponent. It's exactly where I want it to be. Then I go to the bottom. 3 to the negative 3 has to be moved to the top because we want its exponent to become positive. And the x to the negative 6 also has to be moved to the top because we want its exponent to be positive. Notice, anything that had a negative exponent got moved. If it was in the numerator, it got moved to the denominator. If it was in the denominator, it got moved to the numerator. Anything that had a positive exponent stayed exactly where it was. Okay, now everything has only positive exponents. I can finish this up. The first thing I have to do is 3 to the 3rd. Now, either I can do it in my head, 3 times 3 times 3, or I can do it on my calculator. That's what I'm saying. Don't forget, from now on, really, we're going to be using the calculators a lot. So I do suggest you, if you haven't gotten one yet, get yourself a 2-line scientific calculator. Make sure you have a calculator that you could use. You're not supposed to have a graphing calculator, just a regular 2-line scientific calculator. If you're buying one and you're not sure it's what I think is the right thing, don't take it out of the package. Just either send me a picture of it, an email, or bring it to Zoom class and show it to me on your video. Somehow let me see it and I'll let you know if it's the right thing. But you really need a calculator at this point. Once we do square roots and things of that nature, you really have to use a calculator. Okay, going back to this, so we're doing 3 to the 3rd, which is 27, 3 times 3 times 3. Then I have an x to the 6 times an x to the 6. Now I know they're both in the numerator. I'm multiplying them, so I have to add their exponents, so that's x to the 12. And on the bottom, I have 4 to the 3rd, so that gives me 4 times 4 times 4, which is 64. So this would be the answer to the second question. Is there any problems with any of these? Okay, so that pretty much takes us to where we were on Thursday. So we're going to start with new material today. We're really starting our discussion of chapter 6. This was an introduction where we talked about, we reminded ourselves how to work with exponents and specifically what to do when our exponents are negative. One of the things we're going to learn in chapter 6, I'm going to do it a little bit later in the chapter, is what to do when my exponents have fractions in them. We really don't like to work with fractions in our exponents, but there are ways of working with it, and we're going to discuss it, as I said, a little bit later in the chapter. What we're going to be starting with is radicals. Chapter 6 is a chapter on working with radicals. So let's discuss what we mean by a radical, how to work with it, what should we do. This symbol that looks like a check mark with an elongated top is what's called a radical sign. And it's used specifically to indicate that we want to take the square root of a number. For example, if I write radical with a 25, we read that as the square root of 25. And what we mean by that is we're looking for a number that when we multiply it by itself, we get 25. Now, if you think about it, there actually are two numbers that might work. There's 5, because 5 times 5 gives me 25. And there's also negative 5, because if I multiply negative 5 by negative 5, it'll also give me positive 25. A negative times a negative gives me a positive. Now, because if I use a symbol, if I want something like this symbol, radical 25, I don't want it to mean two different things. It can only mean one thing. So we always take this symbol, the radical sign, to mean the positive, what we call the principal square root. So it's always the positive one. In other words, I don't use as an answer negative 5. If I want negative 5, I'd have to put a negative in front of the square root of 25, like that, to get negative 5. Because even though when I multiply negative 5 by negative 5, it does give me 25, this symbol, radical 25, only means the positive answer, the positive 5. Now, when we're talking about negatives, notice we could put a negative on the outside, but we don't put a negative on the inside. This square root of negative 25 doesn't exist in real numbers. We're going to talk about a little later in the chapter a special set of numbers where we can deal with this. But in the real numbers, the numbers that we deal with on a regular basis, we can't deal with the square root of a negative 25. Why? Because there's no real number that when you multiply it by itself will give you a negative 25. It can't be positive 5 because a positive times a positive is positive. And it can't be negative either because negative 5 times negative 5 will give you also positive 25. So in terms of real numbers, this is something that can't be done. We have to have a special new set of numbers. We'll get to it when we talk about it, and I'll tell you then what that set of numbers is called. But in our regular real number system, the one that we use on a regular basis, this is something that can't be done. The radical sign actually is not used only for square root. Before I tell you that, on your calculator, there is any scientific calculator has a square root button. And if you don't know the square root of something, you can always get to your calculator and use your calculator to figure it out. That's why it's so important from now on to have a calculator. Okay, now, this concept of a radical sign is not used only for square roots. You may sometimes see something like this, or something like this. Where there's inside the check mark part, there's a number. That number is called the index of the radical. If you see something with an index of 3, this is read the third root of 8, or sometimes also the cube root of 8, and it means what number times itself 3 times will give me 8, and obviously that answer would be 2. So if no index is written in, then it's understood to be just a regular square root. The index of a regular square root is 2, because when you see the square root of 25, you're looking what number times itself. You're multiplying the number 2 times. 5 times 5. If there's a different number there, that tells you how many times you're multiplying the number. The cube root of 8 is 2, because if I do 2 times 2 times 2, if I multiply the 2 3 times, it'll give me 8. This is read the 5th root of 32. What number times itself how many times? The index is 5. It means it's being multiplied 5 times will give me 32. That also happens to be 2, because if you do 2 times 2, you get 4, times 2 is 8, times 2 is 16, times 2 is 32. If you multiply 2 5 times, you get 32. So this radical sign is a pretty interesting sign, because it indicates you can indicate so many different things. Again, the number inside that check mark is the index. When there's no number, it's understood to be 2. It means it's just a regular square root. What's interesting is that if I have something like this, I can do this. This is read the cube root or third root of negative 64. When your index is an odd number, you can't have a negative inside, because think about it. If you multiply 4 3 times, 4 times 4 is 16, times 4 is 64. The cube root of 64, the third root of 64, is 4. The third root of negative 64 would then be negative 4, because when you take negative 4 times negative 4, it gives you positive 16, and positive 16 times negative 4 gives you the negative 64. So when your index is an odd number, you can have a negative inside. Now, how do we deal with these radicals? The types that we're mostly going to be concerned with are going to be regular square roots. In other words, an index of 2. Every so often you may see something with a different index, but we really concentrate just on plain square roots, because that's what we need most in our studies here. Now, if I give you something like the square root of 121, That is something you can do. 121 is what we call a perfect square, a number that is something times itself. I suggest that you make yourself a list of all the perfect squares starting from 1 until, let's say, 15, so that when you start working with them, you will be able to do some of the problems. If you don't know it, you, of course, can put it into your calculator. The square root of 121 turns out to be 11. I think most people. So 121 is a perfect square. You can take its square root. What happens if your number that you're dealing with is not a perfect square? First, I'm going to deal with numbers, then I'm going to go on to variables. So let's say I gave you something like 50, radical 50. Now, radical 50 isn't a perfect square. Radical 49 is a perfect square. Radical 49 happens to be 7. But radical 50 is not a rational number. It's what we call an irrational number. What does that mean? Well, if I would go to my calculator, which I'm doing right now, and I tried to figure out the square root of 50, I get, on my calculator, 7.0071067,812. It's very long decimal with no pattern to it. Actually, the only reason it stops at this 2 over here is because my calculator only has room for 10 digits. If my calculator had room for 100 digits, the answer would have gone to 100 digits. That's what an irrational number is. An irrational number is a non-ending, non-repeating decimal. And the most common place that you get these irrational numbers is when you take square roots. If you take a square root of a number that is not a perfect square, you're going to get an irrational number. So what do we do with this? Not very comfortable to use such long numbers. What we sometimes do is we just round it off. I said, okay, this is close enough to 7.071. I don't know, I rounded it off to 3 decimal places. It's not an exact answer, but if I'm, let's say I had to measure something and I came up, I had to measure and it came up to this long number, my measurements are not so exact anyhow, so I won't care if it isn't exact, I round it off. That's fine for a lot of science type things or for practical type things. But when we're working in mathematics, we really like exact numbers. We don't like things that are rounded off. So what we sometimes do when we're dealing with these irrational numbers is try to simplify. So let's talk about how do we simplify the radical. Again, you could talk about simplifying cube roots and fifth roots, but I'm going to really stick to square roots. No, I did not do attendance yet. Okay. So let's look at this radical 50 and talk about what do we mean by simplifying a radical. So obviously, if this is a perfect square, then you just take its square root. It's where the number is not a perfect square. What you try to do is you break up the number into 2 pieces, 2 factors. One being a perfect square. In other words, 50 I could break up into 25 and 2. So that the square root of 50 is really the square root of 25 times the square root of 2. Just split it up. One part has to be a perfect square. And the part that's a perfect square, I always put in the front. Now I can go, oh, the square root of 25, I know, that's 5. So this becomes 5 radical 2. This really means that I have the number 5, perfectly good rational number, it's not even a radical, times the square root of 2. And if you had a calculator and you put this number into the calculator, and then you put this number into the calculator, 5 times radical 2, you would see that they would be equal to the same thing. Why is this called simplifying? Because the number inside the radical is much smaller. That's what simplifying a radical means. Try to get your radical as small as it possibly can. The number outside is fine. What you need is a number inside the radical to be as small as possible. Now let's say I gave you the square root of 48. And now 49 is a perfect square. 50 is not, and neither is 48. So let's think how we could break up 48. Well, I'm going to make a list of numbers that multiply to 48. 1 times 48, 2 times 24, 3 times 16, 4 times 12, 6 times 8. I think that's all the combinations of numbers that multiply to 48. When I want to simplify the radical, I want one of the numbers to be a perfect square. And if you look at it, there actually are 2 possibilities that would work. In 3 times 16, 16 is a perfect square. In 4 times 12, 4 is a perfect square. In the other 3, there are no perfect squares. So the question is, which makes more sense to break it up into? The 3 and the 16 or the 4 and the 12? So the rule is, if you can do 2 types of breaking up, separating, pick the one that has the perfect square that's bigger. In other words, since 3 times 16 has a perfect square of 16, that's bigger, that's what we're going to break this 48 into. So here are my 2 radicals. Remember, the first radical goes the perfect square, which is the 16. So the 16 goes in front. The 3 goes in the second. And the square root of 16 is 4. So we simplify the square root of 48 into 4 radical 3. Okay, I'm going to go one step further, and then I'm going to give you something to try. What if I have a variable inside my radical? So let's start with a really simple one. What if I have the square root of x to the 6th? What times itself will give us x to the 6th? Well, if you think about it, it would have to be x to the 3rd times x to the 3rd. Because when you're multiplying variables, what you're doing is you're adding their 2 radicals, their 2 exponents. And if you look, that means the square root of x to the 6th has to be x to the 3rd. And that gives us a good way of figuring it out. In order to do the square root of a variable, all you have to do is take the exponent on the variable and divide it by 2. Why am I dividing by 2? Because my index is 2. If I were to ask you the cube root of x to the 12th, remember this is the cube root or the 3rd root, then I would take the 12 and divide it by 3 because my index is 3. And that would give me x to the 4th, because if I multiply x to the 4th times x to the 4th times x to the 4th, that'll give me x to the 12th. And again, really, I just have to remember, I really have to just concentrate on regular square roots. But remember, the index in a square root is 2. That's why we're dividing the exponents by 2. Now, what happens if I have something like x to the 11th. What happens if my exponent is not an even number? I know if it's an even number, I just have to divide it by 2, and that works. But if I divide 11 by 2, I'm going to either get 5.5 or 11 halves or 5.5. I'm going to get something that's not a whole number. It's going to be either a fraction or a decimal. And when we're simplifying things, we only want whole number exponents. So if I want to do the square root of x to the 11, I have to break that up. I have to split it up in such a way that I get an even exponent, because that's a perfect square, with as part of my answer. And here's what I do. I just subtract 1 from the exponent. X to the 11 could be broken down into x to the 10 and x. I separated, just like I separated, let's say, the 50 into 25 and 2, the x to the 11, I separate into x to the 10 and just x to the 1, which is just x. Remember, I found that out by just subtracting 1 from the exponent. Anytime you have an odd number, all you have to do is take 1 away from it, and you're left with an even number. Now I can simplify it because the square root of x to the 10 divided by 2 is 5. That'll give me x to the 5. No longer inside the radical because I took its square root by dividing its exponent times radical x, because I can't do anything with that. That's the rest of what's left over. So if I were to give you a problem that looks like this, I'm going to do one, then I'm going to give you a couple to try on your own. Suppose I gave you the square root of 18x cubed y4. And I told you to simplify that. How do I go about simplifying something like this? So I'm going to break it up into 2 radicals. My first radical will be all the perfect squares. My second radical will be everything that's left over. And I'm going to do this by looking at each letter and number separately. So I'll start with 18. Now 18 is not a perfect square, but I can break up the 18 into 9 and 2. Notice the 9 goes in the first radical because it's the perfect square. The 2 is what we're left with. When I divide 9 into 18, I'm left with 2. It's not a perfect square. It has to go into the second radical. Then I look at the letters. X to the 3rd. Is it a perfect square? No, because its exponent is odd. So I subtract 1 from the exponent. That gives me x squared for my first radical. And what I'm left with is just a plain x, because 2 and 1 would give me the 3. Then I go to the y4th. Is y4th a perfect square? And the answer is yes. It's a perfect square because its exponent is even. I don't have to split it up. It totally goes in the first radical because the first radical is everything that's a perfect square. So step 1, separate your original number into 2 pieces. The first piece being a perfect square, the second piece, whatever's left over when you divide. Now take the square root of that perfect square. The square root of 9 is 3. And remember, with the exponents, what I'm doing is I'm dividing the exponents by 2. So this is 2 divided by 2 is 1. So this is x to the 1, which I can just write as plain x. And this is 4 divided by 2 is 2, so that's y squared. And times radical 2x. Now you might say, this doesn't look simpler to you than this does. But Simpler means that the number or whatever inside the radical is a smaller number. This is certainly smaller than this. So this is what we call the simplest form of this expression. Okay, let's see if I'm going to give you one to try on your own and while I take attendance. Okay, so here, let me put one on the board. Simplify this. 72 A4 B7 C3. See how much you could simplify that while I take attendance. Okay, so what can we break 72 up into? Well, let's see. 72 is 1 times 72. It's 2 times 36. It's 3 times 24. It's 4 times 18. Not 5, 6. 6 times 12. And 8 times 9. I think that's about it. But I think it should be obvious that the one with the largest square root is right here at the beginning, 2 times 36. 36 is a perfect square. Again, if you don't know that, you should have a list of perfect squares. Make yourself up a list and have it in front of you. And oh, Maya, okay, you're here. Okay, I'm gonna change it. So we're gonna break up the 72, here are my two radicals, into 36, and that's my perfect square, times 2. Usually that's the hardest part, is dealing with the coefficients, because you have to know square roots. But with the variables, all you have to do is make sure they have an even variable. So a to the 4th, that 4 is an even number, so that's a perfect square. It goes in the first radical. The b to the 7, though, 7 is not even, so I have to split it up. I take 1 away from the 7, it gives me b to the 6, and I put a b in my second radical. C to the 3rd, again, I have to take 1 away from that. That'll give me c squared, and that'll leave me c for the second radical. And now this first radical is a perfect square. So I take the square root. The square root of 36 is 6. Remember, with the variables, I just divide their exponents by 2 because my index here is 2. It's understood to be 2. 4 divided by 2 is 2. That gives me a squared. 6 divided by 2 is 3. So it's b to the 3rd. And 2 divided by 2 is 1, which is just c to the 1 or just c. And that's times the 2bc. And this would be your answer in what we call simplest form. So that's what we call simplifying a radical. Changing my all right, so now let's go on to the next thing. We've learned how to simplify radicals. The next thing we're going to do is talk about how do we add and subtract, in other words, combine expressions that have radicals in them. And we're going to see why it was so important for us to be able to simplify the radicals. And the reason we have to simplify radicals is because of the rule for adding. We know when we add algebraic expressions, like if I have a 3x plus a 5x, I can add them because they're considered like terms. They're like terms because they're literal parts. The letter parts are identical. And when I add them, what I do is I just add the numbers that are in front. They're called the coefficients. And this would give me 8x. Whereas if the question would have been 3x plus 5y, we wouldn't have been able to add them because they're not like terms. We can only add like terms. Well, the rule for radicals is almost identical. If I have 3 radical 5 plus 2 radical 5, those are what are called like radicals because what's the radical part are identical. They have exactly the same number inside them. I can add those by just adding the numbers in the front. 3 plus 2 is 5. This becomes 5 radical 5. If my question would have been something like radical 7 plus radical 21, for example, I can't add them and get radical 28. I cannot add these. They are not like radicals. I can only add them if the numbers, and if they're letters, the letters, the variables have to be identical inside the radicals. So we, just like we have to have like terms to add algebraic expressions, to add radicals, we need like radicals. Now, what does that mean? Let me get a book. Suppose I had a question that looks like this. Radical 20 plus 4 radical 80 plus 2 radical 45. Suppose I gave you this kind of an example. And I said, okay, I want you to add them. So your answer should be, you can't add them. They're not like radicals. This has a 20 in it, this has an 80, this has a 45. But we just learned how to simplify radicals. So the first step should be to simplify each of your radicals. And then go back and look if any of your radicals turned out to be like radicals. Well, if you think about 20, you can break up 20 into 4 and 5. I know 20 could be 2 times 10, but 2 and 10 are not a good pair because neither 2 nor 10 is a perfect square. But 4 times 5 is a good choice because 4 is a perfect square, and I can do the square root of 4, that'll give me 2. And of course, the 5 remains inside the radical. So the radical 20 turns out to be 2 radical 5. Okay, now let's go to the radical 80. How can I break up 80? Well, 80, I better give you a bunch of chance. I'm not going to do 2 and 40, but 4 and 20 work. 8 and 10, that's not so good. What about 16 and 5? That'll also work because 16 is a perfect square. And I think that, Of those choices, obviously the 16 and the 5 is the better choice because the perfect square 16 is bigger. So I'm going to do this as plus 4, and I'm going to break this 80 into 16 and 5. And the square root of 16 is 4. So I have this 4 that's now outside the radical. And there was another 4 outside the radical. There was this 4. So I can multiply this 4 times this 4, because you can multiply, as long as they're both outside the radicals, you can multiply them. I can't multiply the 4 times the 80 because the 4 is outside the radical, and the 80 is inside the radical. But I can multiply this 4 by this 4 because they're both outside the radical. So this will give me plus 16 radical 5. The last thing is this radical 45, which you can break up into 9 and 5. That's 9 is a perfect square. The square root of 9 is 3. But remember, there's a 2 in front of it. So this 2, I have to multiply. Remember, there's nothing in between them, so it means multiplication times 3 is 6 radical 5. So it turns out that after I simplified everything, I had a 2 radical 5 plus a 16 radical 5 plus a 6 radical 5. These are all like radicals now. Now I can combine them by just working with the coefficients. 2 plus 16 is 18. 18 plus 6 is 24. So that my final answer comes out to be 24 radical 5. So that's why it was so important to be able to simplify the radicals, because if I can simplify them, then sometimes it'll turn out that what looks like not like radicals are actually like radicals and can be combined. Let's see if I can give you one to try. So let's try this one. 4 radical 8. Okay, plus, minus, minus 2 radical 50, minus 5 radical 72. See if you could simplify and then combine whatever could be combined. Okay, let's see if we can work this out. first of all, can we simplify radical 8? And yes, I can break up the 8 into 4 and 2. And the square root of 4 is 2. But remember, I had this 4 from before that was in front of it, so I have to take the 4 and multiply it. I don't add, I multiply it because there's nothing in between them. If there's no sign, it's understood that the operation should be multiplication. So do 4 times 2 is 8, so this gives me 8 radical 2. Then the 50, okay? We did 50 before, so you should remember this. It breaks up into 25 and 2. And the square root of 25 is 5. But remember, there was a negative 2 in front of it before, so the negative 2 times the 5 gives me negative 10 radical 2. And finally, the 72, we had that one before also. That's 36 and 2. And the square root of 36 is 6. But remember, there's a negative 5 in front of it. Negative 5 times 6 is negative 30 radical 2. So the first thing is I separated each one, I simplified each one on its own. Now I look and I see they are all like radicals because they're all square root of 2. So I work with the numbers in front. I combine the 8 and the negative 10, which gives me negative 2. And negative 2 and negative 30 gives me negative 32. That's my coefficient, and that's times radical 2. I hope you were able to do this. Any questions about that? Okay, so now that we know how to combine or add and subtract radicals, we're going on to the next operation, which is to multiply. And I'm not going to do a division today, but we are going to do multiplication. It turns out when I want to multiply radicals, let's say I want to multiply 2 radical 5 times 3 radical 15, let's say. Suppose I wanted to multiply those 2 radicals. The rule is you do not have to have like radicals. For adding and subtracting, you have to have exactly the same number. And if there are any variables, the same variables exactly inside the radicals. They have to be like radicals. For multiplication, just like you don't need like terms to multiply, you can multiply an x times a y. Here you can multiply the radicals even if they're not like radicals. And the way you do it is you just multiply the numbers that are in front, the coefficients. 2 times 3 is 6. And the numbers inside, 5 times 15. And you get 6 radical 75. And of course, once you finish the multiplication, you then want to try and see if you can simplify. And if you think about it, the square root of 75 could be broken up into 25 and 3. Square root of 25 is 5. So now I multiply the 6 times the 5 so that my final answer is 30 radical 3. So very often at the end of our multiplication, we have to simplify so that we have our answer in simplest form. There are a couple of things that, if you noticed, can make doing these problems a lot quicker. Number one, what if I gave you something like this? The square root of 7 times the square root of 7. Well, according to my rule, what I'm supposed to do is multiply the numbers that are outside. So they're both 1s outside. So that would be 1 times 1. And then multiply the numbers inside, which will give you 49. So you end up with the square root of 49. But the square root of 49 can be simplified. Square root of 49 is just 7. So if I look at my original example, the square root of 7 times the square root of 7 simply gives me 7. And that's a rule that always works. If you multiply the radical by itself, and the two things inside the radical are identical, then your answer is just what's in the radical. If your two numbers are 7 times 7, then your answer is 7. If your question here, let me erase this. If I have the square root of 79 times the square root of 79. Now I actually, if I wanted to, I could do 79 times 79 and then try and take its square root. But I don't have to, because once I know these two numbers are identical, it must mean that my answer is just plain 79 without a radical. Because if you multiply a number, this tells me what number multiplied by itself will give me 79. If I multiply that number by itself, then of course it will give me 79. Or the general rule being the square root of x times the square root of x will always give you just x. We're going to use this because when we're multiplying, if it ever turns out that I have something like this, I don't have to go through all the long steps. I remember the rule and therefore I use it. So let's look at some of the more complicated kind of multiplications that we could get. Number one, we might have something like this. 3 radical 5 times 2 radical 5 minus 7 radical 20. Let's say I gave you that question. Well, you know from these two are not like radicals. I could try and simplify them, but I'm not going to. I'm first going to do the multiplication. I'll simplify at the end if I can. I know that I have a single term multiplying by a binomial. And that means I have to use the distributive property. I'm going to multiply the 3 radical 5 times the 2 radical 5. And then I'll go back and take the 3 radical 5 and multiply it by the negative 7 radical 20. So first, remember the rule. Numbers outside get multiplied together. Numbers inside get multiplied together. So here, the 3 times the 2 give me 6. And now I have the square root of 5 times the square root of 5. But that's my special situation. I'm multiplying a radical by itself. Radical 5 times radical 5 is just plain 5 without a radical. So this first term times the first term gives me 6 times 5. These two can be multiplied together because they're not inside radicals. So that gives me 30. Then I go to the second one. 3 radical 5 times negative 7 radical 20. So I do the 3 times the negative 7 is negative 21. Radical 5 times radical 20 is radical 100. Now it turns out I can simplify the radical 100 also. 100 is a perfect square. The square root of 100 is just plain 10. So now, since this is outside the radical, I can multiply by the 21. That gives me 21 times 10 is 210. And my final answer, since there's no radicals here, they can be combined. 30 minus 210 is negative 180. So my final answer turns out to be a regular rational number. It doesn't have any radicals, so it's rational. Rational means it has square roots in it. It doesn't. So it's a rational number, negative 180. If, I'm going to do one more and then I'm going to give you a couple to try. If I have something like this, suppose I gave you 5 minus 3 radical 2 times 4 plus a 6 radical 2. Where these can't be combined. Don't make the mistake. The 5 minus 3 cannot be combined because the 3 is attached to a radical 2, and the 5 is not. It's sort of like having a 5 minus 3x. They're not like terms. These are not like radicals. That being this case, we still could multiply them because this is one binomial times another binomial. And we know when we're multiplying binomials, we have to use FOIL. So we're going to do FOIL first, outer, inner, last. First would be the 5 times the 4, which is 20. O would be the outer. That would be the 5 times the 6 radical 2. So the 5 I can multiply by the 6. That'll give me 30 because they're both outside radicals. There's nothing to multiply the radical 2 by, so I'll just bring it down. Then I do inner. The negative 3 radical 2 times the 4. So the negative 3 times the 4 gives me negative 12 radical 2. And finally, last, I'm going to do the negative 3 radical 2 times the positive 6 radical 2. So the negative 3 times the 6 is negative 18. And the radical 2 times radical 2, oh, that's my special case. That's just plain 2, not in a radical. Square root of 2 times the square root of 2 is just plain 2. And now I can make this simpler. Negative 18 times 2 is negative 36. So now I combine the like terms. There's a plain 20 that has no radical next to it. That can be added to the negative 36. That gives me negative 16. And then there's a 30 radical 2 minus a 12 radical 2. Those are like radicals. 30 minus 12 gives me 18 radical 2. Now I cannot combine the negative 16 and the 18. They are not like terms. So this is my final answer. So here is where we multiply a monomial by a binomial. Here we multiply 2 binomials. I'm going to give you one to try right now. Let's see if you can do this one. Three radical 7 plus 5, that binomial squared. I'm giving you a few minutes to try that. This is a binomial squared, and we know when we have a binomial squared, we have to write it twice. We have to write 3 radical 7 plus 5 times 3 radical 7 plus 5 so that we can do the FOIL. We must do FOIL on this because it is a binomial times a binomial. Okay, let's be careful now. 3 radical 7 times 3 radical 7, that's first. 3 times 3 is 9. Radical 7 times radical 7, that's our special case. That just gives me 7. And 9 times 7 gives me 63 because the 7 is no longer inside a radical sign. Okay, that's first. Now we have outer. 3 radical 7 times positive 5. So I have to multiply the 3 times the 5, which is 15, and that gives me 15 radical 7. Then I do inner. 5 times 3 radical 7. Again, the 5 and the 3 are outside. They get multiplied together. That's 15 radical 7. And last is 5 times 5, which is plus 25. And now I just have to combine the like terms. Now the 63 and the 25 are like terms. They're both just plain numbers, no radicals. That gives me 88. And the 15 radical 7 and the 15 radical 7 together give me 30 radical 7. Remember, when I'm adding, I just add the numbers on the outside. These I cannot be combined because the 88 doesn't have any radical 7 next to it. So my final answer is 88 plus 30 radical 7. I hope most of you got that answer. Okay, so that takes us through basically adding, subtracting, and multiplying of square roots of radicals. Again, we concentrate on working with radicals, square roots. In other words, where our index is 2. Of course, next time we're going to talk about what happens when we want to divide. And we're also going to talk about what happens when my exponents, we've talked about having exponents that are whole numbers. We've talked about exponents that are negative. What could it mean that we have fractional exponents? It's another thing we have to talk about. And then we're going to talk about what happens when we have an equation that has a radical in it. And also our special numbers, what happens when we have square roots with negatives in them. Those are all things that are coming up in this chapter, but we're going to start out with dividing. Since we know how to add, subtract, and multiply, let's talk about dividing next time as our first step. Don't forget to look on Delta Math to get all those assignments. What I'm going to do is I think I'm just going to extend the date of all the assignments until the end of the term so that whenever you can get to an assignment, just get to it. Again, your final mark is not only your midterm, it's not only your tests, it includes the assignments, the homework assignments. That's all going to be included as part of your mark. The homework, and my personal tests, whether they're on Blackboard or on Delta Math, all together comprise 30% of your grade. So it's very important that you get those as high as number on those grades as you can. So I see most everybody has done the midterm at this point, and most of the marks are good. If you didn't do well on the midterm, you want to take it over, I may give you a chance to do that if you get in touch with me. If you didn't get to do the midterm yet and you still have to do it, get in touch with me. I probably will take some points off. Okay, Dominic, I'm gonna extend, and I'm going to extend the date on the homeworks on all of them. I'm just going to go back and change all the due dates on the homework to the very last week of the term. I mean, obviously I have to have it by the end of the term because then that's when I figure out your mark, but I'm not going to penalize people because they didn't do the homework. If you didn't get to do some of the homework, look at them by tonight. I hope to have that done, to see that you can get extra time you can do the homeworks, and if you didn't complete them so you can get the full credit for that. Does anybody have any questions that they want to ask me? Again, look for the homework. I'm going to do another homework starting there. We have homeworks through number 9. I'm going to be giving you a number 10 probably by tomorrow. So look for those homeworks. Again, I'm not giving you a due date, but when they come on, it means that that's on the material that we've just currently learned. If there are no other questions, I'm going to end this session for all of us. Any questions? Okay. So have a good day, and I will.
Bye-bye.
Bye. Thanks.
Bye.
Have a
good day, Professor.
Bye.
Thanks for coming. I hope to see you again on Thursday.
Everybody see you on Thursday.
If you have any questions, make sure you ask.
Good day.
Bye-bye.